This is the screencast for section 6.3, example 7, simulating horizontal motion. So right there, in the title of this example, horizontal motion means that your vertical motion is going to stay the same. So I'm going to take this opportunity to compare a few different scenarios here. First of all, if we were going to look at his position according to time, before we knew how to do parametrics, that would be in a rectangular coordinates, we would be graphing something like y equals negative 0.1 x cubed minus 20x squared, etc. And so I've done that on my calculator here. X stood for time, which in the function is represented by t, and y is the position, but in the function is represented by s. So I can see where, Gary is walking. He changes directions here at 3.8 seconds, which has a y value, a position of negative 9.9 because he was walking maybe left. And then he's walking right because he's, it's along a horizontal line. So he's walking in a positive direction, hits a maximum here at 9.5 seconds, and then has a position of negative 1.23, and then turns around and goes the other way. Also, you can see here that he started at time t equals 0. He started at 8.5, is it feet? Meters away. So now in parametric mode, we have the ability to actually see his motion along a horizontal line. Now you get to pick what you want that horizontal line to be. If you want him to walk along the x-axis, then you might want to pick y equals 0 for your horizontal line. Or if you want him to walk along the line y equals 3, Johnny Cash song just rang in my head. Anyway, y equals 3, you can make his vertical position always 3. So y would always equal 3 in this case. So that's what I chose. So now I put this on my calculator, and I changed my t-step to 0.1 just so it's moving slow enough. The calculator's calculating every 0.1 second so I can see his motion. And I let my knowledge of function mode instruct me as to what I wanted my window to be. So now in parametric mode, x is going to represent his position, which we know is along a horizontal line. T is going to represent time, and y is going to represent his height, which if he's walking around along a horizontal line is always the same, and I chose 3. So since x represents position, and I'm already have graphed this in function mode, I can see that some positions that are important are, around negative 10, maybe position negative 1. So I chose my x-min to be negative 15 and my x-max to be 20. My y-min, since his height is always the same, I just chose my y-min to be negative 10 and my y-max to be positive 10, just because. So let's watch his motion. Wait, you can't see that motion. So here's another trick. For parametric graphs, sometimes it's nice to go to the left of the x-coordinate and hit enter twice. That will graph with a little circle so you can see Gary's motion. So let's try that again. So now he's walking left. Then, nope, he's going to come back around. Walking right. And then he's turning, see, that was almost at negative 1 and whatever, like we said before, and then walked left again. So on the graphs that so we can see how function mode and parametric mode are related. So for example, in parametric or in function mode, we found out that at time about 3.9 or 3.8, so I'm going to hit trace 3.9. At time 3.9 seconds, his position is negative 9.91, which is what we got when we were in function mode. And then, of course, the height is always going to be 3. Or maybe let's go with t equals 0. At time 0, he started off at a position of 8.5 seconds, but that's a specifically horizontal position. So my x-coordinate is 8.5 when my time is 0, and the y-coordinate is going to be 3. Or what about the other time he changes directions? So at 9.4 seconds, The position is negative 1.23, almost 24, yep. And then, so that would be also reflected by our function mode. Now, the direction said, use parametric equations and grapher to simulate his motion, estimate the times when Gary changes direction. You do not have to do this in function mode to estimate those times. All you would be able to do is start at t equals 0 and then trace. Keep going along in time to find out. So he's moving left, still moving left, still moving left. But now, okay, still moving left, still moving left, still moving left. Okay, this is getting boring. Come on. Change direction. You can see his position, the x-coordinate, is now starting to change direction. There we go. So now we're going, his x position is getting closer to the y-axis now. So he changed directions at about 3.8 seconds, which again is what we had said. So you could keep doing that. You do not have to graph in function mode first. Now the other thing that I want to show you, because it's really hard to show a still image of this and see all of his motion. Well, if I choose to make the y-coordinate t, so adjust y to time, I will see his position, his vertical position, change by 0.1 every second. So for example, I did that on the calculator ahead of time, and I said that if y1 equals t, now I can see his position expanded vertically to kind of see how he moved horizontally, but I can see it all at once. So for example, at time 0, my height I made it y equals 0, and his position was 8.5, just like we had discussed. Now at time 3.8, when he's changing directions, I made his height also 3.8 so that I can just see his path as we're going. And then same with the other time that he changed directions, which is at time 9.4. His position was still negative 1.23, so very close to the y-axis. It was just expanded vertically so I could see that happening. You may choose whichever method works best for you, or as you'll see in the now try problem, sometimes the situation lends itself to which way is best. The now try problem is simulating a foot race. Ben can sprint at 24 feet per second. Jerry doesn't sprint quite as fast, but Ben gives Jerry a 10-foot head start. The parametric equations can be used to model the race. So basically, you've got Jerry here who's going to sprint faster, and Ben who has 10 feet less to travel than Jerry does. When I put my functions into the y equals, I want to have the circles representing Ben and Jerry running so I can see that happen. Now the window, time equals 0, how many seconds is it going to take either of them to run, 100 yards? So if they run 24 feet per second and I want them to run 100 yards, that's going to be 300 feet. So I want my position, x max, to be 300 feet. I'm going to go definitely farther than that. So let's do my x max 350. And then as far as my t min is 0, my t max, again, how long is it going to take them to run 300 feet? Well, let's see. It would take Jerry 5 seconds to run 100, so 15 seconds. I'm going to try 20 seconds. Let's go crazy. Let's go 30 seconds. Alright, so then my x-min can be, it has to be bigger than negative 10, so let's start with negative 15 is fine. Well, let's go to negative 20 so I can see it a little bit better. Now as far as my y-min and my y-max, Jerry's running along the line, y equals 3. Ben is running along, y equals 5. So maybe I'll change my y-min to negative 5. Alright, so let's graph that. Now here's the problem. I don't see a finish line here. I want to be able to see that. That's the beauty of parametrics, is you can kind of see their motion. So I'm going to add to this problem. I'm going to put in x3 and y3. Their finish line. Their finish line is going to have a vertical is a vertical finish line, so it has a horizontal position of exactly 300 feet. Now, as far as its y coordinate, I can't make its y coordinate specific. So I want to draw this finish line vertically very fast. So I want to draw it faster than they're going to get there. So I'm going to draw it 10 times faster than the amount of time passing by. And then I'm going to have them run at a t-step of 0.5. I tried 0.05 and I fell asleep while they were running. So instead I'm going to do 0.5 so they run a little bit faster. Let's see how this works. So there's your vertical line growing very fast. Good. So the finish line is done. They're still running. Ben has passed over Jerry. Jerry's only at y equals 3. Ben's this one. So Ben finished. Jerry finished. So you saw their path, and you can rerun that as many times as you want. And you can even see how Ben started 10 feet back. Now part B asks who is ahead after 3 seconds and by how much. So if I hit trace and I find 3 seconds, first of all, that would be Jerry. And then if I hit up, I will go to Ben's curve. Nope. There's Ben's curve. The other one was the finish line. So Jerry is at 60 feet. Ben is at 62 feet. So Ben is ahead by 2 feet.